Hello, everyone. Today we're going to cover the topics of boundary conditions. So boundary condition, it's uh, kind of simple section in this chapter, but it's a very important. So we will spend one whole class to discuss the boundary conditions. And in the future homeworks and exams, you will use this boundary condition frequently. So first of all, in the typical problems in this class, we sometimes use source charge distribution rho, and you want to find the electric field E it produces. So sometimes we can use Gauss law if the symmetry is perfect, then we can use Gauss law. For example, if you have a spherical charge distribution or sometimes a pillbox or um, let's say a cylinder or something, then that's a perfect symmetry shape. And then sometimes Gauss law will bring you a lot of convenience. If it's not in the symmetry case, generally you can take advantage to calculate the potential first, because we know in Gauss law, what did you calculate? It's E, which is electric field. We have done a lot of examples in previous sections to see how to use Gauss law to calculate electric field. But if you cannot use Gauss law in some cases, actually in most of the cases, you cannot use Gauss law, then it is general for you to take advantage to calculate the potential first, which is V, and then use potential. Once you get the potential, you can calculate electric field line by just take the derivative of potentials. So we have learned three quantities or basic quantities: rho, E, and V. So rho is charge density or charge distribution. E is electric field, and V is the potential. So for those three important or fundamental quantities of electrostatics, we have derived 6 formulas between each two of them, which is shown here. For example, you can have a formula to calculate rho based on E. You can also calculate E based on rho. You can also calculate V based on E, or calculate E based on V. And also you have two equations to calculate rho based on V and calculate V based on rho. So for those three important quantities, between each of them, between each pair of them, we have two equations. So it guarantees no matter which quantity we have, we can always get the other two quantities. And based on these 6 equations or the relationships between or among these 3 basic quantities, there's something in general. Okay, so there are 2 things in general which are based on the experimental observations. The first thing is the principle of superposition, or a broad general rule applying to all electromagnetic forces. For example, if you have several different charges, if you want to calculate, let's say you have charges Q1, Q2, you want to calculate a potential here, then you can calculate the potential based on Q1 and then calculate the potential based on Q2. If you sum them up, you will get the total potential here. And the same thing, it's not only for potential, it's the same thing is for electrostatic force, electric field. You can always calculate the electrostatic feature at the potential based on one charge and based on another charge and another charge. So you sum them up, you will get the total quantity, the total value of the quantity you want to calculate. So this is the general rule of principle of superposition. This is the first rule. Second rule is Coulomb's law. You can always use the Coulomb's law to calculate electric field, electric potential. Okay, these are the two basic laws and the relationships among the three basic quantities. Okay, and the electric field always undergo a discontinuity when you cross a surface charge. Let's say if the surface charge density is sigma. In fact, it's a simple matter to find the amount by which E changes such a boundary. Okay, now let's focus on the E changes at a boundary, which is the main focus on this class. Let's see, when you have a charged surface, what will happen for E, the electric field, and later we will see the potential crossing the boundary. Okay, now first, let's say if we have a surface which is shown here, let's draw a very small pillbox on the surface. Then if you draw the pillbox small enough, this box will be this pillbox will be a rectangular shape, and you have the pillbox shown here. We draw it big because we want you to see it clearly, but you can imagine if you draw a very small pillbox, what will happen? So first, what will happen in the pillbox is, first, we can apply Gauss law to this pillbox. So the integral, the surface integral of the whole pillbox of E equals to 1 over epsilon times Q, which is a charge. And Q could be written in sigma times A. Sigma is the charge density, A is the area. So in the figure, we can see if you do the surface integral of electric field for the entire surfaces of the pillbox, then you get 1 over epsilon times sigma A. Let's say if the charge density is sigma, then sigma times the surface area A is the charge. So that's the Gauss law. And A is the area of pillbox lid, or the area of the pillbox covered surface, because the surface is shown in a curve structure. The part of the pillbox covered is A. And if sigma varies from point to point to the surface that is curved, we must pick A to be extremely small. Then the sigma indicate, in this case, the sigma indicate the charge density just at this pillbox location. And then the sides of the pillbox contribute nothing to the flux. For example, let's see, this side and this side, it doesn't contribute anything to the flux. And in the limit as thickness epsilon goes to 0, we are left with E above subtracted by E below equals to 1 over epsilon times sigma. Okay, so if you remember Gauss law, when you do a surface integral of E, so we know the direction of E at this pillbox is going up or down. So if it's going up at the top, it's positive, and if it's going down, actually it depends on the sign of your charge. Is it positive charge or negative charge? But we can define going up to be positive direction of E, and at the bottom going down to be the positive. So at the bottom going up is also the positive direction of E. But no matter it's let's say the sigma or charge density is positive or negative charges, the E at this position should always either go up or going down. So there's no side or parallel component of E, which is a parallel to this pillbox surface or the top pillbox surface. So it's always going up or down. So in this case, the side, 1, 2, 3, 4, the 4 sides of the pillbox doesn't contribute any E to the Gauss law or the Gauss equation. So the Gauss equation here becomes E above subtracted by E below equals to 1 over epsilon sigma A. So, okay. So from the, let's write it one more step. So this is Gauss equation. From Gauss equation, Gauss law, if you want to calculate the integral of E, what you can do here is E above, let's say E above, I'll use EA stand for E above times A because it's going up. The electric field line is going up, which is perpendicular to the surface of A. So E times A plus E perpendicular B times A. But let's say the direction of E is going up. However, the direction of the bottom surface is going down. That's the normal direction of the surface at the bottom of the pillbox. So it should be negative because when you do the dot product of E and A at the bottom surface, they're in the opposite direction. So the dot product should be a negative value, which makes the sign here to be negative. And for the side, it contributes to the integral as 0. So you only have the contributions from the top surface and bottom surface. So E above times A subtracted by E above times E below times A equals to 1 over epsilon naught sigma A. Sigma times A means Q. And then you canceled all of the A, and then you get the equation shown here, 2.31. So E above perpendicular denotes the component of E that is perpendicular to the surface immediately above, which is shown here. And E below is the same at the surface, at the lower surface or the other side of the surface. And for consistency, we let upward be positive direction for the E. But remember that for E, positive direction means going up, but for the surface A, going positive means going out. So in the upper lid of the pillbox, positive surface means going up, but in the bottom, positive surface means going down because going out means the positive direction when you do the surface integral. In particular, where there's no surface charge, E perpendicular is continuous, as for instance, the surface of uniformly charged solid surface. Okay, so if we look at this equation, we notice that if there's no charge density here, or charge density equals to 0, then E above equals to E below, which means if no surface charge, then E perpendicular above and below the surface is the same. The tangential component of E is always continuous. For if we apply 2.19, then the integral of the let's say, okay, so the integral of the electric equals to 0 to thin rectangular loop. The end gives nothing, and the side gives E above equals to E below in the perpendicular direction. Okay, so let's see this integral. If we find a line integral just above and below the surface, and if we find, we define this circle, or this rectangle of the line integral to be very thin. And then first, the, let's see. Okay, so first, the rectangular loop gives nothing, and the side gives E above, perpendicular E above times L, which is here on the above side of the rectangle. And then at the bottom of the rectangle, you get a negative E parallel times L, because your direction of E is still going to the left, but your direction of the line going to the right. So it yields in a negative sign. Okay, so so in this figure, if you do the line integral, you know it equals to 0, which means E above equals to E below in a in a parallel direction to the surface. Okay, so the boundary condition can be combined into the single form if you combine the parallel and perpendicular equations of the boundary condition. Then you get the difference between electric field lines above a surface and below a surface equals to 1 over epsilon times sigma, and the direction is in the normal direction, which is in this direction, which is perpendicular to the surface. Okay, so that's the boundary condition for electric field at any boundary or any surface. Now, that's for electric field. Now let's see the potential boundary condition. The potential, meanwhile, is continuous across any boundary, because V above subtracted by V below equals to the integral of E times dl, the line integral. As the path length shrinks to 0 when the distance from A to B becomes almost 0 or 0, then the integral becomes 0 if the path length shrinks to 0, or if the thickness of the surface is very thin, to as thin as 0, then V above equals the V below. However, the gradient of V inherits the discontinuous in E, because E equals to the negative gradient of V. So V above subtracted by V below equals to 1 over epsilon sigma in the direction of normal direction. But it's there's a negative sign because E equals the negative gradient of V. So this is the same thing. This equation 2.35 is the same thing as the equation of 2.33. So it's just written, the 2.33 equation in another format of V, and the relationship between V and E is so simple. It's just E equals negative gradient of V. Or more conveniently, we can write it in this way. Partial potential above over partial normal, let's say, vector subtracted by partial V below over partial N, it equals to 1 over epsilon times sigma in a negative sign, where partial V over partial N equals to the gradient of V in the normal direction. So it's just another format of the same equation shown here. So you just need to remember one format of the equation. Then you can derive all the other equations either in 2.36 or 2.33. So that's the boundary condition for E and V, the electric field and electric potential. Please note that these boundary conditions relate the field and the potential just above and just below the surface. For example, the derivatives in 2.36 are limiting values as we approach the surface from either side. Okay, so that's all about the boundary condition. So from the boundary condition, we have learned the relationship between up and below electric field lines and up and below electric potentials, electrostatic potentials. So this is a very useful lecture. Please remember all the conclusions in this lecture. Let's say especially these equations and these equations. That's for electric potential. And then for electric field, this is the most important equations. Okay, so a general summarize is on the, let's say on the charged surface, if on the surface there are some charge densities, then for electric field, there might be a jump or discontinuity due to the charge distribution. But for electric potential, it's always continuous, no matter if there is a charge density on this surface or not. So the electric potential, it's always continuous, or V above equals to V below. So that's the main points for boundary conditions. Okay, that's all for this lecture. Thank you.